Hello, my name is Edward Jin, and this is my first lab for Physics 2211 revolving around constant velocity. First, I'm going to introduce some ideas and points to help understand this presentation and the purpose of it. I will be identifying Newton's first and second laws and the concept of net force. Newton's first law states that an object at rest will stay at rest and an object in motion will remain in motion unless the object is acted upon by a non-zero net force. Newton's second law essentially states that the acceleration of an object is solely dependent on two key factors, being the net force that acts upon the object and the mass of the object itself. Net force is the combination of all of the forces acting upon the object over a period of time. Since the net force is zero in this experiment, the object will not be speeding up or slowing down. The purpose of this experiment is to observe the motion of the object with a constant velocity due to no net force and compare the results using tracker and glow script for computation. Additionally, in this experiment, we will be assuming friction and air resistance does not act on the ball, as we are trying to observe the motion of an object with a constant velocity. Here are the formulas we will be using. The first formula, force equals mass times acceleration, relates to the Newton's second, as it shows the relationship between acceleration and force along with mass. The second and third formulas are the position update and velocity update formulas that we will be using in GlowScript. Here is my video for the experiment where we will be moving a ball at a constant velocity. Moving on, we can see the data from the tracker in which I plotted every point for each frame the ball moved. Here, you can observe the distance versus time graph has a positive constant slope. And here we have the code for GlowScript and the output for the position versus time graph of the ball. So for the GlowScript code, I had to set some initial values such as the ball position, ball velocity, and delta t. Here you can see that I set the ball's position to 0.0007 and 0.587 for the ball's initial velocity, which I calculated using the velocity formula I had previously mentioned. Also, I set the delta t value to the time between each frame in the tracker video, which was approximately 0.0165 seconds. Here, we can see that the net force is zero, as there were no external forces acting on the ball, which is why I set all the values to zero. As the ball is in constant velocity, we know there are no external forces acting on the ball. I have also changed the ball position update and ball velocity update calculations by using the position and velocity update formulas I have mentioned in the previous slides. Now, here we have a graph showing the time versus distance for the ball calculated by GlowScript using our previous formulas and the tracker in which I manually gathered the data. As we can see in this graph, they both seem to have a positive slope with the computational media giving a straight line as opposed to the tracker with some inconsistencies. This makes sense as we are accounting for outside forces that might have influenced the output for this graph, such as some human errors I may have made, such as clicking on the ball to gather data for the tracker. This seems to be very plausible as it is not feasible for an individual to click exactly where the ball center is for every single frame. In conclusion, we were able to find very similar trends between the experimental tracker and the computed values using GlowScript revolving around the motion of constant velocity. To touch on the what-if portion of changing the x-axis and flipping them, I believe the only change would be to the distance versus time graph itself, as the slope would be the exact same, but it would just be a negative, as the relationship between time and distance would stay the same, given the exact same numbers, but the distance would just have a flipped sign. In the observed case, when the net force is zero, it means that the sum of all pushes and pulls or forces acting on the object cancel each other out. I would say that it is not possible for me to say exactly how many pushes or pulls are acting on the object, as we do not see most of the exact data and we do not have the tools that may be required to determine these values. This concludes my lab report. Thank you.